And then our next speaker is James Walsh from the University of Massachusetts, and he will talk about mounting samples under pressure in a diamond anvil cell. Welcome, James. There we go.
See that now? So that's my
Yep, you can see it. Very good.
Okay. Excellent. Thank you so much. And thank you for the invitation to speak today. I was asked to give a workshop overview of the steps involved in loading a diamond anvil cell for a high pressure experiment. And I think this is an important thing to talk about, because a lot of people, I think, when confronted with the idea of going into high pressure, they have this fear, the fear of ultimately breaking diamonds. And that comes from, I think, not really understanding enough and not wanting to wade into experiments where they might destroy equipment. Or if they don't have the equipment yet, they might be worried about what they should purchase. There's so much variety. Stas touched on this. There are many different types of diamond anvil cell. I think, you know, new scientists have fears about committing to the wrong equipment. So what I hope today to do is to allay a lot of those fears and show you that actually you can get into high pressure. There's a lot of support, there's a lot of community support. You can always ask questions. That's going to be the ultimate message, I hope, is that there are people you can reach out to if you are stuck. But really, you should be able to make a good plan for how you can get into high pressure and learn enough to know what you need to buy and how to do everything. So that's the goal of the slides that I've put together. There'll be a lot of overlap actually with previous slides, which I hope is a good thing and reinforces to you that this is a manageable knowledge field. Okay, so I'll start, as I always do, with a quick overview of what the diamond anvil cell is. This has already been touched on, as we know, but the diamond anvil cell really, despite the complexity of all these different types of cell and the shapes of the cell and the conical opening and everything else, they all boil down to really just you're driving two diamonds together in a very aligned, precise way. So you want a uniaxial force to bring the diamonds together, and you want them to not slip or tilt. And if you can achieve that, you can do a high pressure experiment. So all diamond anvil cells, no matter what they look like, really boil down to this simple picture of you've got two diamond anvils that you're pushing together. We use a gasket material between the diamonds. We don't just squash the sample with two anvils. I think in the very early days, that's how the experiments were done. That doesn't lead to a uniform hydrostatic pressure around the sample. It leads to a very uniaxial pressure, which is not really what we want. You can't really do single crystal. You can imagine how a single crystal experiment would go if you just squashed it with two diamonds. So instead we use a gasket material, and this is just something that that really makes up the walls of the sample space. So all this will boil down even further into just the sample space, which is a cylindrical void that we put the sample into. And as we collapse the diamonds, as we drive them together with whatever force applying system, whether that's screws or a gas membrane or whatever, piezo, what we're actually doing is collapsing that void. And as we do that, that will increase the pressure through the pressure transmitting medium, fills up all the spaces, and then that pressure gets applied to the sample. And so we always fall back to this P equals F over A, pressure equals force over area. The higher pressure you want to go to, generally the lower, the smaller that culet face. That's the name of the polished face that's small, the pointy end of the diamond. The smaller that is, the higher pressure you can go to. So there's a question about what's the limit for how low in pressure you can go. If you know that you want to work below 5 GPa, for example, you would probably purchase large culets on the order of, say, 500 to 1000 microns. If you know you want to go to 10 to 30 GPa, 300 microns, to megabar, 100 microns. So these are things, if you don't, I think Stas had some good slides with details on that. But if not, just reach out and ask. That's one place that you could go wrong. You could buy the wrong size diamonds, because if you really want to work at low pressures, it's a waste to use 300 microns, because now you're limiting your sample size for really no benefit. Okay. So the considerations, I would say, people reach out to me all the time. I want to get into high pressure, but I'm overfaced with the choice and what type of cells are available and what. I'm trying to minimize the video account, but they're overfaced by all the choice of all the selection and variety of diamond anvil cells. These, I would say, the considerations that we typically go through. I think the most important thing is that you want a cell that's easy to use. And it's very easy, depending which vendors you speak to be talked into buying a system or a diamond anvil cell with assorted features that does something that you don't really need. And that will overcomplicate things, and you end up with an over-engineered cell. So this is how I started, actually. So I got a cell from Allmax that could do resistive heating. It had a membrane, attachments for cryostats, all these other things that we didn't really need, and it ended up making that cell quite difficult to work with because it was over-engineered. Really, all we needed to do was just go to pressure, and that was it. We were using laser heating and everything else that didn't require anything special in the cell. And so what we use now, so my lab, basically all of our cells are these IBX80 type. This is what Stas introduced. I don't mean to endorse DAC tools, but everything that we use basically comes from DAC tools. Stas is an expert in the field, and so there are many companies to choose from. I do endorse DAC tools, but I don't get paid for that. So that's just my opinion. So we use the IBX80 because it really is that middle ground. Stas made a comment that some customers are afraid of the spherical seats, which is used for correction. I'm one of those customers, so I always ask for the IBX80, but there are of course reasons why spherical seats make sense. But that's an example of maybe that's over-engineered for a new user. Just make sure that you get a cell that does what you need to do and not much more, and you'll have an easier time, I think. The other consideration is, can you get the data that you need with that cell? Again, Stas gave an excellent overview. I was taking notes furiously when he was talking about the different cell, seat, and anvil configurations, because really what it ultimately comes down to, and especially in single crystal diffraction, is that conical aperture. What 2 theta value can you get to and get good data? You want atomic resolution, that extra 10 degrees, 20 degrees is going to make a huge difference. And so I think for single crystal, people who are interested in collecting single crystal data, you should probably be prioritizing, can I get 80 or 90 degrees of, you probably won't be able to get 90 with a solid cell, but aim for 80 degrees and buy the right seats and anvil combinations and everything else to get to that. Similarly, if you're not really interested in high resolution data, maybe 70 degrees is enough and you'll get a more stable cell, and you'll be fine with that. Is it compatible with all the instruments I want to use it with? So for me, this is the consideration is I want it to work on my Rigaku Synergy S. I would say most cells really, the collision sphere is pretty big on the Synergy S, which is great. And so that means that really most cells fit. You'd have to find some really weird big cell for it to be too big for the instrument. And there's probably something that could be done in that case. But for the standard amount of space, Fraser touched on this, most cells will fit within that. And then the other consideration that we have is that we often do a lot of work at the synchrotron. We'll do preliminary work on our Synergy S and then take it to the synchrotron. And so we want to have cell diameters and dimensions that work with the gas membranes, for example, at the beamline. And so that's what the I believe, stands for. It's an imperial measurement. And so it works with the most, excuse me, the most instruments at the synchrotron. And the final consideration, is it well made? I've had experience with probably 4 or 5 different companies over my time of being in charge of purchasing DACs, and they're not all always well made. So go with a reputable company that's recommended by a company that you trust. And I think DAC tools being recommended by Rigaku, I would agree, you get solid, well-made cells that are not going to let you down. So I would say that's an important consideration. I've worked with people who bought not very good cells, and I won't name companies, but that can make a difference, and it can make it very frustrating for new users when your chewed screw won't, isn't usable, so you don't use that screw. That's not what you want. Okay. So let's say that you are trying to start a new lab. So I feel like a lot of people that are at this kind of workshop are interested in high pressure may not already have the tools that you need, and they just want to know, if I wanted to do a high pressure experiment tomorrow on this crystal that I have, what would I need to be able to do that in-house? And I would say that this is really your minimum requirements. An important thing to have is a microscope. And so there are 2 things about the microscope I would say are important if you're buying a new one, or if you're looking around campus or wherever. there are two things I think are important. One, it should be binocular. You want to be able to get depth perception because a lot of the work that you're doing under the microscope requires that. So if you only have, you know, one eye, you're not going to get quite as good depth perception. It can still be done, but if you have the option, try and get binocular. The other thing is a large working distance between the objective lens and your sample, because often these diamonds are seated low into a cell. You need that clearance and you need your hands to get in. And so that's something that typically is not standard. And so if you're buying a new microscope, make sure you ask for a large working distance or try and find one that already has a large working distance. There are various little tools and pieces that you need. So Q-tips for cleaning the anvils and various things. Acupuncture needles, these are actually very difficult to get hold of. For some reason, you need a license, an acupuncture therapist license for many places. So you can find them online, but they often won't sell to you. If you have trouble, reach out to me. I can tell you where I got them from. But these are super useful. If you already have a crystallography lab, you might already use these. They're really good for manipulating very small samples and moving them between places. You'll need a micrometer. So this appears in pretty much all high pressure labs. This is just a way of measuring physically thicknesses. And so here we're looking at the thickness of an indented gasket. And so that's a really useful tool that you'll need. And then the other thing, so Stas touched on this, and I'll talk a little bit about it, is a drill. And so you won't get far with a high pressure experiment if you can't drill your gasket. I'll go through the steps of preparing a cell, and we'll talk about this in a bit more detail, but you really do need access to some way to drill your gaskets after indenting them to make that sample space. And so this is the tool that we bought. This is from Almax. I believe it was designed by Rainy Bowley. You can see his name 3D printed on the side. This is basically a slight variation of the instrument that Stas mentioned from Hylozoic products, the micro EDM, and there is a long wait line. So I probably would have gone with that one if there was an option. This one is a bit more expensive. I paid somewhere on the region of $20,000 for this, but we needed something to be able to drill. Didn't quite have deep enough pockets for the laser drill, which is excellent. If you have it, if you have the money for that, you should get a laser drill. I'm saving up for one, but we needed to be able to drill. And so this really is probably the only way that you'll be able to do this, especially given that the micro drill is not really available anymore. So I'll talk about how this works, but this is probably the thing you would at least have to buy to be able to do everything in-house. Now, it might be the case that your department, if you're at a university, this is, that your campus, sorry, might have people in other departments who already have some of this equipment. And so check geology, and a lot of mineral physicists use this equipment. That's really where the field of high pressure came from. And a lot of physics groups now are using high pressure diamond anvil cells. So you might already have this on campus that you would be able to go and use. But if not, I would say that this would be the minimum requirements to get started. Now, there are some things that make life easier, or open up certain experiments that you wouldn't be able to do otherwise, and that requires equipment, and it's usually expensive equipment. So this I wouldn't say is starter equipment, but maybe it is. Maybe you've got a big grant and you're trying to get into high pressure and you just want to jump in and have everything you need. These are the things that I would say are probably out of the price range of a beginner, but you should know about them because they do open up interesting experiments. So a pressure gas loader. So this is for the pressure medium. I'll touch on this again later. But as Stas mentioned, actually, there are two ways that you can get gases, which are really the most hydrostatic pressure medium. And that's something that for single crystal people is probably the most critical. To get those gases into the cell, you have to use some tricks, and that's either by loading it with high pressure. So you put the whole cell into a chamber and you just put so much pressure that it condenses that gas. And then when you get enough of it that it flows into the gasket, you can then close it with some remote operation. You pinch the diamonds and you trap that gas at some pressure, and then you recycle the gas. That works really well. It's an expensive and very large instrument. Some universities have these. You should check. Again, the geology departments might already have a gas loader at your particular institution. And there's a relative, it's hazardous because you're working with very high pressure. These are very safely designed, but that's a consideration that you should make. A much more, a less hazardous and more accessible way of doing gas loading would be with the cryogenic gas loader. So in this case, you're using liquid nitrogen bath to condense a gas. And so really this only works with gases that will condense below 77 Kelvin. So argon is typically used in this way. And so there's no high pressure involved. You're just using very low temperature to condense your gas into a liquid, which then goes into the sample space. So this gives you access to really the best hydrostatic pressure transmitting media. We say quasi-hydrostatic. Nothing really is hydrostatic at high pressure, but that's important for the reasons, again, that Stas illustrated nicely with those very sharp diffraction spots in sodium chloride. If you want really good data, you don't want strain. Strain's going to broaden your peaks, and if you want high resolution data at high pressure, that can quickly prevent you from doing that. And so something that you almost certainly will have on campus, whether it's set up to look at DACs, may require some modification, but some spectroscopic table, some spectroscopic analysis tools, in particular UV-Vis, if you want to look at the R1 fluorescence of ruby as a pressure standard, or Raman, if you want to. You can use Raman to measure pressure actually on the diamond edge, or you want to measure Raman spectra of your sample. You know, that can be a quick, more accessible way to do sample measurements. But of course, this is an X-ray diffraction workshop, so you probably want to see the crystal structure. And so the other thing, this is obscured by my videos that I don't know how to minimize, but this is the laser drill. And so Stas mentioned this. It's too rich for my blood right now, but it's really a great tool for not just machining gaskets, but for machining other pieces that we use in particular. And so I'll mention that later. But again, it's not required. It just enhances the experience, I would say. Makes a lot of things easy because EDM drilling can be tricky. Okay, so I want to go through now for people, you know, maybe you've done diamond anvil cell experiments, maybe you haven't, and you just want to know what are the steps that would be taken. And I hope that this demystifies the process for you in some way and gives you confidence that you'll be able to do this. So this is step one, cleaning and mounting the anvils. For many people, you may never do this. So if you're inheriting a diamond anvil cell, or you're buying a new diamond anvil cell, you might not ever have to actually glue the anvil itself to the seat, but it's an important step for reasons, again, Stas touched on. The gluing the anvil, the diamond, to the seat. You want that to be done in a very precise way so that that culet, the pointy bit of the diamond, aligns well with the whole cell base. If you don't, you can introduce, you know, tilting, and that can come back and bite you during the experiment. So alignment is critical in this step. And if you get this from a company, so Allmax can do this. When you buy anvils and seats, they'll glue them together for you usually for a small fee, but they do a good job of that. Where it's important, especially these days, more people are moving to these Bowler Allmax type seats where the diamond sits in that conical bore of the seat itself, that there can be tilt in the diamond. So you have to check before you glue and dry everything that that's well aligned. And so we do that actually with a laser jig. This is from Allmax. And I'm not getting into this, but it allows you to verify before you pin everything in place and apply the glue that culet is flat, basically. And so how do you glue? We use JB Weld. I think most groups, it would have to be a special case why you would not want to just use JB Weld. The two-part epoxy, you mix it up, you know, add it around the diamond, that will dry usually over a day. You can speed it up by putting it on a hot plate if you're in a pinch, but usually leave it for a day and it will dry, and then you've got your anvil and seats together. Okay, so then the next step is, I really would like to be able to move that video. I can't. I think I remember what I'm showing. But the next step is to center the diamonds. This is something that you have to learn how to do. Some groups don't do it, and that certainly will come back and bite you sometimes, especially if your cell has some rotation during compression. Make the assumption that as you bring the cell together, the piston into the cylinder or whatever design you have, that there might be some rotation. If your diamonds are not aligned on what we call the center of compression, or center of rotation, sorry, then that rotation can induce misalignment of the culets, and that can cause all kinds of problems. So the first step you should do, whether you've, you know, if you've inherited a cell that someone says is centered, you should check it. And this is the way that you would check it. The first thing is to bring the diamonds close together. This is a very scary picture. You know, we know that if diamonds touch, they can break each other. That's not entirely true. It's not immediate if they come into contact, but it really doesn't take much force once they're touching for one to break the other, or for both of them to break. But we need to get them close so that when we look through the microscope, we can see the relative alignment of the culettes. So the first thing you do is bring them into alignment, which is relatively simple. You're moving the set screws. Hopefully you have access to both anvils at the same time. You bring those into alignment, and I can't move my laser pointer past this point because I can't even grab this video to move it. But on the top right panel, you're looking at culettes that have been aligned, and to a novice, you might say, great, they're aligned, good to go. But there is some virtual rotation center of your cell piston and cylinder that you can't see, but that's the point that everything rotates around. And so to test, you do a 180-degree rotation just to see how bad it is. And as long as you're pretty close, you should end up with something that looks like, I think, the bottom right picture, which is where you have misaligned culettes that are clearly not overlaid anymore. But that's telling you, you can work back from that and say, okay, well then the rotation center was not at the center of the culettes. That would have been nice. My job would be done now if it was, but it's not. That means I need to move my culettes, and of course you need to move both of them. And so basically you split the difference, and you want to move them both back halfway towards the other one. And then in theory, you should then be on the rotation center. So now when you rotate 180 degrees back, you should not see that eclipsing, or you want to see an eclipsed pair of culettes. So this is, I've spent a bit of time on that because it's, I think, a critical reason for why most things go wrong. When you indent and then you drill and you see that, oh, why have my, it was centered hole on one side, but it's not on the other side. That means that your diamonds shifted, but they looked good under the microscope. That could be one reason. You might be introducing some rotation as you compress that's causing that problem. So this is the routine that you should get used to. And only when you can rotate one of the anvils relative to the other, or really the whole half of the cell relative to the other, and you don't see misalignment. I forget how I started the sentence, but that's the case that you want to get to, that you see fully eclipsed, even when you do a 180-degree rotation. Yeah, so then you would iterate the process. You may not always get it right the first time. I usually have to go a couple of times and go back to the original rotation until I see absolutely no shift. So that's centering the cell. Okay, so the next step then would be to pre-indent the gasket. This is an important step. Stas gives some details on why. We start with, I'm showing here a rhenium chip. This has actually already been indented by the looks of it, but originally this would just be a 250 micron thick square rhenium chip. We rest that on one of the anvils, and so you can see actually there's some wax that keeps it in place because it's easy for that to fall off. And that's a very good way to break diamonds, is when that falls off and you don't realize, and then you close the cell up. So the wax keeps it in place. And what we are trying to do is compress that between the two anvils so that we get a pre-indentation. And so rest the gasket onto that lower anvil, bring the top in, and then look through the microscope, and you'll see something like this. And so what we're seeing here is we're looking through the back side of a diamond. So this is the inside of the diamond, if you will, and this is the culet. So this circular-ish polished face is the culet, and it's touching rhenium. So this grainy feature is the surface of the rhenium gasket, but it's just touching. And so that's where we start from. And so typically we'll tighten the screws. We don't tighten them, but just enough so that there's some give, and that's what we say is the beginning. And so we typically will mark the screws. So you put a Sharpie over the screw head, a line that starts on the screw head and onto the cell, and that says, 0 degrees. That's where you started from. That's important because there is some repeatability to these cells. If you take notes and you see that for this indentation thickness, I turned 2/3 of a full turn, you'll probably find, as long as everything else stays the same, that you can just use that in future. So it's worth making notes on these things because they are repeatable for a given cell. So that's where you start from. You've got your diamond in contact with the gasket. And so one thing I don't think I mentioned, I did here in the text. This is what scares people the most, because this is usually when people break diamonds. Either the gasket falls off and they bring the diamonds together and they look and they hope to see the rhenium, but they actually see light and broken diamonds. That's one thing that can go wrong. So always make sure that you can look from the side of the cell to make sure the gasket hasn't slipped. But that's that's really the most dangerous part. The second most dangerous part is actually tightening itself. And so this is where we start to now tighten these screws. So as we tighten the screws, we're bringing the cell together, applying a force to the anvils that's then going to push the diamond tips into the rhenium and push that away. That rhenium will start to flow away from the culettes. And we're trying to get to the point where we've reached, still got some elasticity or some plasticity left in the gasket for it to collapse during the experiment, but we've got rid of most of that softness. So we're trying to find that sweet spot. And so this is something that you get from experience really, but generally you want to go to pressures of around 20 to 25 if you have a way of measuring the pressure between the culet and the gasket. This is a very rough rule of thumb, and this might actually only apply to 300 micron gaskets, but this is the danger, is that you put too much force, way more than you need, and you've really thinned out the gasket already, and you keep going. Well, when the gasket is really thin, it's not offering any cushion, and so you're essentially pushing diamond into diamond at that point, and that's when things can break. So start slow. So I'm showing here a cell. This has right-handed and left-handed screws, doesn't really matter. This is, I think, an old, this is something that was introduced in the early days, with the idea being that if it's balanced and perfectly symmetrical, you'll get a more even pressure. I don't think that really matters. And so a lot of cells nowadays are just all right-handed. Make sure you know. That's another way that people can make mistakes. They don't realize or they're incorrect in which way they're turning the screws. They're applying pressure when they think they're reducing pressure. So make sure you understand which are the right-handed and left-handed, or if they're all right-handed. That might simplify things. But start slow, very small increments, and you'll start to build up the pressure between the two anvils. I would start with 1/16 turns, and I would turn opposing screws. So you'll get more balance that way, rather than going clockwise around, because now you're kind of daddying it down in an uneven way. If you use the opposite screws, you can, you're applying a more equal force as you go. And so what you'll see, again, this is hidden for me, sorry, but you'll start to see, hopefully, you can see on this picture where it is a halo that forms around the culet. So the culet doesn't change, that's diamond, but you'll start to see a dark region appear around the side. And that's just because, if you imagine this is the anvil and we're pushing into the rhenium, because of this pavilion angle, the deeper we go, it starts to rise up the edge of that pavilion. So that, what we call a halo, is a measure really of how far into the gasket you are. So if things are going well and it feels good, it feels like you've got resistance, but it's smooth, and you're increasing the pressure, you're pushing the diamonds, you're indenting the gasket, you'll see that halo grow and grow. And so I can just about see the edge of one of the halos here. This is basically, you get to a certain point where that halo stops growing, and you're probably at the point then where you should stop, take it out and measure it and see how thin you've gone with the gasket. And so that's why we use the micrometer. So in this case, we've taken it from 250 down to 17 microns. This is pretty thin. We typically aim, as Stas said in one of his slides, for this kind of pressure, 300 microns to 30 GPa, we should be more on the order of 20 to 30 microns. So we kind of pushed past that limit. Luckily nothing broke in this example, but now we know that we're at the right thickness, we can move on. There's this misconception, I think, for a lot of people, that you have to do this in one shot, all or nothing. You've got to tighten it as much as you can to the exact right amount, because you don't get to put it back in. You absolutely can put the gasket back in. I think it's important for very, very high pressures, because the repeatability of where the gasket goes, and compressing it and releasing it could cause problems for very high pressure experiments where these minor imperfections can have a bigger effect. So you can imagine, if you don't put the gasket back exactly where it was, now the pavilion faces are not really matching where they used to be. I think it can be an issue for megabar experiments, but for low pressure, absolutely take it out. Don't go too far, take it out. Okay, I really only indented to 100. I put it back. You go a little bit further the next time. Now I'm at 50. Okay, I'm going to push it a little bit further. That's absolutely fine. For low pressure experiments, I've done that all the time. It will not cause any serious problems. Another thing, washers are important. Things can go wrong if your washers are old and rusty and they don't have that give. The whole point of the washers is to dampen the force of the screws, and if they don't have any dampening effect, they're just flat, they flatten out with age. If you have a really old cell that you've dug out from somewhere, maybe buy new washers, because those Belleville washers are trying to give you more room for error. or to make the process slower, so that a turn, a lot of that force goes into compressing the washers rather than the diamonds. So that just gives you a bit more room to breathe. So you want washers, you want them to be equal on all screws so that you're applying equal force and everything else. So that's something that's often overlooked, but they're super cheap to get hold of. So I would look into that. It can be a very important thing. I think I've said everything on this slide. Okay, so then the next step is drilling the sample space. Obviously, you have to do this. You cannot do a high pressure experiment if you cannot drill a hole in your gasket. And so this is really I would say the limiting factor for most people getting into high pressure and being able to do it. You need access to some kind of drill or a laser machining drill. But the goal is just to put the hole right in the center of the gasket. Stas alluded to this. It can be really tricky. Not so much with the laser system, that's foolproof, but with the EDM, it can be kind of tricky. But this is a slightly different design to the traditional machine that Stas showed, and it aims to make this process a bit simpler. So you're moving the sample under a microscope to see where the drill actually goes, and then you can align your gasket with that point, and then you can move it back under the drill, and you should be good. And we've actually got this working quite nicely. It does work repeatably. And so this is just a small copper wire, and there's a motorized stage here, or a motor that's moving this entire stage perfectly vertically. And then when it makes contact with the gasket, it will basically ablate the gasket material to the thickness of whatever wire you put on. And so this is another benefit of the laser drill, is that you can basically pick what hole size you want. With an EDM, you're limited to what you can purchase as a gauge for the wire that you're using. So this is I'm not going into too much detail with this, but this is an important aspect of high pressure. You need to have a way to drill the sample space. So this is so the laser drill. This is the one at HPCAT, which is at the Advanced Photon Source in Chicago. So this is a user facility for high pressure. And this is where this instrument was developed. It's now commercialized through DAC tools. It's useful. So I'm showing on the right how it drills a hole in the gasket. So you can type in whatever diameter you want, you center it, it goes around and basically ablates with the laser now the rhenium, and then we do another pass just to clean up the edges. We can also use it for other things in high pressure. So not so much of relevance probably to this audience, but we do a lot of synthesis at high pressure. That's not single crystal, so that's really powder. And so we like our pressure medium. We don't mind that it's not so hydrostatic. What we really need is thermal insulation, because we're laser heating. We don't want to heat the diamonds. And so this is just using the same tool to cut out discs of magnesium oxide, which we can then use as a pressure transmitting medium. It also makes it very simple to load in the glove box, because we're using solid pieces rather than messing with liquids and things like that. Okay, so the next step would be to load the sample. So you've got your sample space. You can put that gasket back onto the one of the anvils, the lower anvil, but it doesn't really matter which one. But now that seat's back in place, and so you've got most of your sample space. You've got the diamond floor, and then those walls of the rhenium gasket, and that's what we want to put everything in. And then we're going to bring the top diamond and close it up. So this, crystallographers probably already have these skills. It's something that's difficult for new students because you're working on such a small scale. But acupuncture needles can be used to select a nice crystal. You can use all the same techniques you would for selecting a good single crystal. Won't go into that, but then you want to lift that and put it onto, the way I load usually is to put onto one of the diamond anvils, not the same size as the gasket. That can be awkward trying to put it into a gasket space. You often knock off the gasket. So you don't need to do that. Just put it on the other diamond. It won't go anywhere on these scales. The forces will keep it in place. And if you need to add any rubies, I'll mention this on the next slide, I think. You can add those as well. Just put them next to the sample. And so on this, I'm showing this is the top anvil, and this would be, actually, I don't know what this picture is. Seat the gasket back. Yeah, so hopefully this is just showing the gasket being on the other anvil. So that's how I would recommend doing this. I've seen people struggle with trying to put a single crystal into a gasket. So as long as it's in the center of that top anvil, it's going to be in the center of the sample space. assuming everything else is centered, which it should be. You can also do this in a glove box. You know, this ramps up the difficulty somewhat, but it's absolutely achievable. Just requires practice. You've got to, you know, put in the work to get good at this. But you can do all of this in an inert atmosphere. That's no problem. The tricky part is getting the pressure medium in. I'm not going to go into too much detail on that, but you can do all the sample load, and you can close the cell up in a glove box and keep it completely oxygen free. I'm showing a picture. So again, this is not really relevant to this workshop because it's not a single crystal. This is a pressed flake of something that we then did laser heating on it at the APS, but this is actually encapsulated in a sandwich of those MgO discs. And that's something that is easier to do in the glove box than liquid loading or even gas loading. So if you can, get a binocular microscope built into your glove box. If you don't have that, you can use a digital camera and a screen. This is how I first started learning. You just don't have that depth perception. It's like using a monocular microscope, but you can deal with it. So that's another option for loading the sample. You can do in a glove box, no problem. The pressure calibrant, this is important. I'll make one or two comments because it's already been touched on by Fraser and Stas, but the standard usually is to use optical calibration. You can also use X-ray calibration. You can look at the unit cell of something that's been calibrated to get to pressure, but often it's more convenient to use an optical method, and for that, ruby spheres are pretty common. I think most groups will use this unless there's a reason to use something else. Rubies as spheres, we actually buy these from Betsa, which is I think a French company. You should, so basically there's a plug for Betsa because we had some trouble with a batch that we got from EasyLab. I don't want to, you know, say don't get ruby spheres from EasyLab. Maybe they fix this now, but the quality of ruby spheres can vary between vendors. So speak to people and say, where do you get them from, and take a look, because they can be very different. The other important thing is that when you're measuring, you should always measure, especially if you need very precise pressures. And for crystallography experiments, you really want to know exactly what pressure you're at. The reference that you are using, that value, so this is pre-filled in this website that we all use. Stas mentioned it, it's on his slides. That value should be on your ruby that you put into the DAC. So once you've selected a good ruby, use that same one, because there can be some variance. I don't know if it's caused by size or what, but it's not always 694.11. So that really should be something that you pre-populate with your exact value. And of course, this is using literature equations and values. But that's an important thing that I see people often neglect, and you can be reporting the wrong pressures in that way. Not by too much probably, but just make sure that if you can, that your reference ruby value is of the ruby that you used. Okay. I'm not seeing any questions because I can't see that screen, but I can get to that at the end.
You don't have any questions.
Okay, great. I don't know if that's a good thing. So the last thing I'll touch on is adding the pressure transmitting medium. So this is another limiting factor really for new labs, is how do you actually get something around your crystal that's going to be hydrostatic and give you good, or quasi-hydrostatic and give you good data. What most people start with, at least, is liquids. And there are various liquids you can choose, and there are some good references talking about the suitability of these to what pressures, how hydrostatic they are. That's the thing you want to avoid ultimately, is that at some point, these, even though the liquids, they will start to behave badly, introduce strain to your sample and diminish your data. But the reason people start with them is because they're pretty simple to get hold of. These are all simple, chemicals that don't really require any hazardous or tricky ways to load. This is the way I do it. You add a sample drop to the gasket side, which has nothing in, and then you bring the other side into it. And at some point it's going to, break the surface tension of that bubble, and hopefully nothing moves. Sometimes it does. And then you've trapped in that liquid with the gasket. If you put the sample in the gasket, not only is that a bit more tricky to do because the gasket's in the way while you're actually loading it, I tend to find that when you add the droplet, that kind of washes the sample away. So try it this way. I've had most success with this method. I won't belabor this. Stas has already covered this basically with the same points that I did, or I have. But the pro is really that it's easy to use. But for single crystal, you really should think about whether you can gas load, because the hydrostatic at relatively low pressures, but really not beyond 10 GPa for most. That varies, but you won't find anything that you can load in this way that's really good for much more than 10 GPa. And in fact, they can often become very poorly hydrostatic above 10 GPa. The other option is solids. Again, Stas mentioned this. Sodium chloride is a common solid. I've talked about using MgO as a pressure medium. It's even easier to load than liquids because you're not having to do it quickly before the thing evaporates. And you can mix it if you're doing polycrystalline samples or flakes like we use often. That's relatively easy to load. And it can also offer thermal insulation if you need that, if you're doing laser heating. And it's also built-in pressure standard, so sometimes you don't even need Ruby. You know, if you have the equation of state and you don't need to know precisely, because it's certainly less accurate than other methods, but if you just need to know roughly what GPa you're at for preliminary measurements, you can just use the X-ray lattice parameters of the pressure medium itself. But this is good because it's not really hydrostatic under any condition. I'll correct that because I noticed Stas said that it's not so bad at low pressures. So maybe sodium chloride is okay if you're at pretty low pressures, but just like the liquids, beyond a certain point, it's not going to be hydrostatic. And you're probably not going to maintain your single crystal. So the best way to do it, if you can, and this might mean sending an email to people who have this, or one of these two ways of doing gas loading, but really the gold standard for data for single crystal would be loading with hydrogen or helium, you know, a light gas, because that's going to give you, to the highest pressures, a hydrostatic. And when we say hydrostatic or quasi-hydrostatic, we mean that not that the pressure is equal in all of the sample space, that's not really achievable, but that at any point, in other words, at the crystal, the pressure that it's experiencing is the same. So you can imagine a very tall column of water. At the surface, it would be low pressure. The very bottom, under the, you know, the weight of all the water, it's going to be higher pressure. So it's not the same pressure throughout the entire column of water, but at any point, those forces should be equal. And so that's really what you want for single crystal, because otherwise you get strain. The downside that you should consider is that certain maybe porous systems, if you're looking at MOFs, for example, you can actually be changing the chemistry of what you're looking at, because the pressure medium can actually enter the sample, and that might not be what you want. But otherwise, it's going to give you the best data. So it can be hazardous in some senses, but not if you're doing it safely and with people who know what they're doing. But it really does give you better data if you can do it. And so then the final slide would be that you close the sample up and you're ready to go. Once you've closed it up and you're at some pressure, you can basically leave the cell indefinitely. You don't have to do this on the morning of your experiment. You know, some people I think have this preconceived notion that the pressure is going to go somewhere, or it's going to go higher or lower. It won't. You can keep these for years. I've looked at cells that we've kept at megabar pressures and they don't change. Once they're stabilized, you're good to go. So you can do this anytime before the data collection and not worry too much about things changing. And so this hopefully will lead into what Pierre is about to talk about, which is the actual data collection, which brings up its own issues that you need to be aware of. And actually, so just one final thing, a bonus slide. Again, coming back to this idea that a lot of people are afraid of breaking diamonds and that prevents them from jumping in and trying it. I can see where that comes from, especially if you only have 2 anvils and you break them, well, then you can't do high pressure anymore. So these are I've broken many diamonds in my time. These are the reasons, and I've seen many other people break many other diamonds. These are the reasons that tend to pop up over and over. One is the gasket slipping out of place when you're indenting. So new users who are doing this by themselves, they remember all the steps, but they might look, you know, they're checking out the cell in different ways and that gasket falls off, they don't realize, and they bring the 2 diamonds together. So always check, you know, I like to get down at the side of the desk and make sure that the gasket's still in place as I'm bringing the diamond in, so that doesn't happen. If your anvils are so far out of alignment at the beginning, and this is possible sometimes, so that, let's say the culettes are really far off. When you're looking through one culet, what you're actually looking at, you don't see the other culet, you're just seeing the pavilion face of the lower diamond, right? So you're looking down here. And so you actually can bring into contact with the diamond without even seeing it coming, because you're expecting to see at some point this lower culet will come into focus. It never does, you're so far off, crash. So just make sure that as long as you center by eye on the macro scale, that shouldn't happen. Not using the set screw. So, okay, I wrote this as a how to break down. The set screws are important. They define a limit of how far the piston can go. So use those as your safety. And if you're closing the cell, have the set screw engaged. It's going to hit the set screw well before it hits the diamonds, just in case you need a bit more strength than you realized. That can cause troubles. And then the last thing, breaking diamonds by going to higher pressures than they're designed to go. If you have a pressure calibrant, this shouldn't happen. You'll know the limits of your diamonds, but at the same time, sometimes this is worth it. And so we've actually broken diamonds in experiments where we knew we were going to break them, but we wanted that extra data, especially a beamline where really in total the costs are bigger, even though we're not paying those costs, but that data can sometimes be worth getting to. Probably not in a home lab. So make sure you're using a calibrant and know the limits of your diamonds. Okay, so minute over, but that's the slides, and I'll invite any questions. You might need to relay them to me because I'm not seeing that part of the thing.
There are no questions in the Q&A,
Okay.
James.
Great.
Thank you very much. We are scheduled for a short break. We'll be back at 15 after the hour.
Okay, I'll just say if anyone has any questions, feel free to email me. I'm always fielding questions, and we want to get people into the field, so please don't be afraid, no matter how silly the question is. Just reach out.
And just so you know, your email address has been posted in the chat.
Good.